Hi there, welcome to a new video series on Laplace transforms. The first question is, why study Laplace transforms? Well, it helps us solve a great deal of complex problems. It does that by taking a differential equation, which is presented in the time domain, and then we can take that and we can convert it into an algebraic equation. And algebraic equations are generally much easier to solve compared to differential equations. So this transform allows us to convert a differential equation to an algebraic equation and make it much easier to solve like that. So in doing so, we can analyze systems like circuits, control systems, and mechanical vibrations in a much easier manner, and we can use it and apply it to systems where we need it to be stable over a long period of time. For example, the autopilot on a plane. We want the autopilot to be very responsive, and we want it to be stable over a long period of time. So in analyzing and designing these kinds of systems, we find it very useful to actually apply Laplace transforms. So what is a Laplace transform? What does it look like mathematically? So what happens is we have a function in the time domain, essentially some function of time, and we convert it. We apply a transformation to this function, and the way we write it is that it's a capital letter L, and this L represents the Laplace transform of the function. And what is it equal to? What we do is we take our function of t, we multiply it by an exponential function, and that exponent is e to the minus st, and then we integrate it from 0 to infinity with the constant of integration, or rather the integration variable being t. So that's what a Laplace transform is. So when we do that, we can see that we're integrating everything with respect to t, and then what we find is that we come out with some function of s, because if t and we remove the t, we integrate it, substitute values of t, etc. So what's going to happen is that we're going to end up with some function of s. And this s is just a parameter, okay? It's just a parameter, and this s is assumed to be a large parameter such that this exponent converges. So let's do an example of this. What is the simplest case? So the simplest case is we have a function of t that's just a constant, okay? So that's our function, and we want to take the Laplace transform of it. So this is the definition of the Laplace transform, how it works, and we simply just apply it. So the Laplace transform, this capital letter L as we have written it, and our function is a, just a constant. Now this is equal to the integral from 0 to infinity. Remember that this is both in terms of t, and our function, which is f of t, and that's just a. And we multiply this by e to the power minus st dt. And then we just simply integrate. So the integral of e to the power st is e to the minus st. And we have an inner function, so we have to account for that inner function. And we bring that out, so we have a over s. So this minus s is the constant. And then we're integrating this from 0 to infinity. So now if we substitute infinity here for t, so we have e to the power minus infinity, and if we just draw the graph of e to the minus st, it looks something like that. So there's t on the x-axis here. So we can see that as t goes to infinity, this function will simply just approach 0. So e to the minus infinity there on the top is simply just going to give us 0. So what we're left with, if we bring out this minus a over s outside, we're left with a over s. Integration bounds, firstly it's 0, as we just explained with the infinity. Then we have minus, then e to the power 0, and e to the power 0 is 1. And then we're left with minus a over s times minus 1, which is just a over s. So this is the Laplace transform of some kind of function. So if we have a function that's, let's just say, for example, f of t is equal to 2, okay? So the Laplace transform of 2 is just a over s, or rather 2 over s. So it's as simple as that. So we can now actually develop a series of standard Laplace transform for a variety of functions in a different form. For example, if we have an exponential function, f of t is equal to e to the power at, and we want to find the Laplace transform of this function, all we would do is apply its definition. So we have the Laplace transform of e to the power at, and it's defined as the integral from 0 to infinity of now this function, which is e to the power at, and we multiply it by e to the minus st. We call the definition, so we can just go back and refer to the definition again. There's it. F of t multiplied by e to the minus st. So there's your f of t, and there's your e to the minus st. So we carry on in this manner. So we have the integral from 0 to infinity, and we just add the exponents by the laws of exponents. So what I'm going to do is I'm just going to take minus t out as a common factor. So if I do that, so there's the minus t as the common factor. So what I'm left with is essentially s minus a. I've just done this because it just makes it easier to integrate it. So if I do integrate it now, so I get integral of e to the minus this exponent, that just remains as is. That's s minus a t, and then I account for the inner function, so I need to multiply it by 1 over, rather minus 1 over s minus a, and this is all integrated with respect from 0 to infinity. So as before, e to the power minus infinity will just give us 0. So I will bring out this minus 1 over s minus a here. And we're going to have 0 since the infinity is there. And as was before, e to the power 0 is 1. So this Laplace transform, minus times minus gives us a plus. So that's 1 over s minus a. So the Laplace transform of an exponential function is just 1 over s minus a. So we can carry on with a variety of different functions like this. So let's just look at a few more. So what we want to do now is find the Laplace transform of the function. F of t is equal to sine at, and also the function where it's equal to cos of at. So how do we go about doing this? Well, we have to use our definition of the Laplace transform, which is of ft. We take integral from 0 to infinity of f of t times e to the minus st dt. Now we can substitute these things in directly, and we'll get there, but we'll have to use integration by parts, and it becomes a bit complex to do that. So we can use a shortcut here, that is to use complex numbers. So we can recall that e to the power j theta, that's e to the power j theta, is equal to cos theta plus j sine theta. So that's what we're going to do. We're going to find the Laplace transform of this, and we can see how we can relate it somehow. So just to put in the at there, so instead of theta, so I'll have e to the power j at, which is equal to cos at plus j sine at. So what we're doing now is we are finding the Laplace transform of e to the power j at. And what this gives us, using the definition, integral from 0 to infinity of e to the power j at multiplied by e to the power minus st dt. And we proceed as we had done in the previous example. We just add the indices. So we have the integral from 0 to infinity of e to the power. I take out minus t as a common factor. So I have s minus ja and dt. So I can quite easily integrate this. And when I do, integral of the exponent remains the same, s minus ja times t. And I account for the inner fraction of fraction, so I have minus 1 over s minus ja. And this is integrated from 0 to infinity. So if I do actually integrate this, firstly I bring out the constant here, so I have minus 1 over s minus ja. Integral of e to the infinity is 0, as we had said several times now, and then we're going to be left with minus 1. Minus and a minus gives us a plus, so I'm left with 1 over s minus ja. So what I'm going to do is get rid of the j that's in the denominator, and I have to multiply by its conjugate to do that, rationalizing the denominator as they call it. So I multiplied by s plus ja. That's both the numerator and the denominator. So when I do that, I get s plus ja in the numerator, and multiplying it out, got s times s, that gives me s squared. And we have now ja times ja. So a times a is going to give us a squared, firstly. Now this j times j is just the square root of minus 1 squared, because that's what j is. J is the square root of minus 1. So the square root and the square essentially cancel, and we're left with minus 1. So we have minus 1 times minus 1, which gives us plus 1. So if we split this out now, we split it out, we just, in terms of the numerator, we separate out using the plus step. So we have s over s squared plus a squared, and then we have plus. Now j, I've just written that there, and then a over s squared plus a squared. Look at its form. We have a real part, which corresponds to cos of at, and we have an imaginary part, which corresponds to sine at. And is this not what we had seen here? Okay, the polar form of this exponent, this complex number. So that's exactly it. That's exactly it. So this real part corresponds to the Laplace transform of cos at, and this imaginary part corresponds to the Laplace transform of sine at. Let's just write it out. The Laplace transform of cos at is equal to s over s squared plus a squared, and the Laplace transform of sine at that's just equal to a over s squared plus a squared. So this is a generic equation we can use to simply get the Laplace transform of any kind of cos or sine function. So the last standard Laplace transform that we're going to look at is the function of t, in which we have t to the power n. Okay, so this would be your polynomial functions, for example, t to the power 4 or t squared or whatever it is the case. So n is just a generic exponent here. So as we had done previously, so to find the Laplace transform of t to the power n, what we do is apply the definition as before, integral from 0 to infinity, the function, which in this case is t to the power n, and multiplied by e to the power minus st dt. So this now is a bit more challenging to integrate. There's no real kind of shortcut here, so we have to use integration by parts. So if we just remind ourselves what is integration by parts, we have to have two functions, for example, uv, right? So we say that the integral of u dv is equal to uv minus the integral of v du. So since this is now from 0 to infinity, it's a definite integral, so we have to integrate this thing from 0 to infinity like that. So you have to say one thing is u and one thing is v. So what we'll do is that we'll say that u is equal to t to the power n. That means that du is equal to n times t to the power n minus 1 dt. Then we'll say that dv is that portion. So that's u and that's v. So v is equal to e to the minus st dt. So that means that dv, we have to integrate it. Sorry, this is dv. So that means that v is equal to just minus 1 over s times e to the power minus st. So now we just put it into our formula for integration by parts, and we get our expression. So let's call this original expression, this Laplace transform, let's call that I n. So the integral of n, where n is this exponent here. So we'll say that I n is equal to, firstly, uv. So we have t to the power n, then we have v. So we're multiplying this by minus 1 over s times e to the minus st, and we're integrating this from 0 to infinity. So the next term here, we have to say the integral of v du. So there's v and there's du. So firstly, we have this minus. So we have n here, and we have minus 1 over s. So this minus and this minus becomes a plus. Then we write the n here. Then we have this s. Then the integral from 0 to infinity. And v is e to the minus st. Okay, let's write that afterward. But firstly, we have this du. So we have this t to the n minus 1. Let's write that first. Tn minus 1. And then we have this e to the minus st dt. So let's evaluate the first part of this integral. So if we do that, well, we have e to the infinity. So that's going to approach 0. So even though we have t here, we said that s is quite large. S is a large value such that this whole thing converges. So that means that this first term is going to approach 0 because our assumption is predicated on this s being large. Then we have t to the n, the 0. So 0 to the power n is just 0. So we're going to have 0 there again. 0 minus 0 is 0. So all we're left with is this second term. Okay, this second term. So I'm just going to write it here. We're left with in is equal to this entire thing being 0. And what we're left with is this n over s, then this integral from 0 to infinity, t to the n minus 1, e to the minus st dt. So if we look at this integral, we see that it's in a certain form. And if we compare it to our original integral that we are looking at, that's I on the top here, we see we have t to the power n times e to the minus st. And if we look at the bottom, right, we have t to the n minus 1 times e to the minus st. So what is different between these two? Well, there's not much except that instead of n, we have n minus 1. So what we can do is we can just write this whole expression here, okay, this whole expression as just I, and instead of n, we'll say n minus 1. We've just grouped it like that. So that's what I'm going to write here. I can write that in is equal to n over s times in minus 1. And then now, if I were to write it one less, right? So I look on the left-hand side here, this in. So if I now replace this n here with n minus 1, then I do the same thing with the right-hand side. I get n minus 1 over s times in minus 1. So if I do it again, on the left-hand side, I replace this n minus 1 with n minus 2. Then it means on the right-hand side, I'll have n minus 1 minus 1, which will give me n minus 2 over s times in minus 3. Sorry, this should be n minus 2 here. So we can carry on with this trend. We can now see that I n minus 3 is equal to n minus 3 divided by s times I n minus 4. So this is going to carry on forever until we reach I0 essentially, because that's the smallest value of n that we can have. And this we're going to see is going to equal to n. Now, minus, we can see here that this 3 is the same as that. So it's going to be minus n minus 1, okay, 1 less than that, divided by s. Now, what's this I here? Is there such a thing now as this n minus 4? What's left there? Well, the answer is nothing. Because if we think about what I0 actually is, if we go here on the top, we have I n here, we have I0. So let's just look at I0. I'll just write it here. So I0 is just going to be integral from 0 to infinity of t to the power 0 times e to the minus st dt. And anything to the power 0 is just 1, okay? And the Laplace transform, as we had seen earlier, the Laplace transform of a constant, first example, is just a over s. So in this case here, the constant is 1. So that means that I0 is essentially just 1 over s. That's what it is. So what we're going to do now is just write it as we see it here. So this In is equal to n over s, I'm just copying this, times In minus 1. But what is In minus 1? In minus 1 is this thing. So we can substitute that in there. So what I'm left with is now this n minus 1 divided by s times In minus 2. But what is this In minus, sorry, there should be a 1 over s here as well. This In minus 2 is now this n minus 2 over s times In minus 3. So I can replace that there. So I have n minus 2 divided by s times In minus 3. And I replace this In minus 3 with n minus 3 over s times In minus 4. So I have n minus 3 over s In minus 4. So it's going to carry on like that. It's just going to carry on like that. We will keep replacing until we get to I0. And what is I0? We substitute that expression in for I0, which is n minus 1 over s times 1 over s. Okay? So what that means is that we have n times n minus 1 times n minus 2 and so on. It goes on in that way. So that is just n factorial divided by, and we have s now that's being multiplied n times. So n stops there. So we have s to the power n. And we have an additional s here because of this I0 or this 1 over s. So we have to add 1 to it. So that is it. That is essentially what In is equal to. And In was the thing that we were wanting to solve. That was the Laplace transform. So what this result says that the Laplace transform of t to the power n, which is our original function, is simply equal to n factorial divided by s to the power n plus 1. So this is how we get the Laplace transform, standard Laplace transform, for a variety of different functions. In the upcoming videos, we're going to consider a number of theorems and other ways of considering and analyzing the Laplace transform for a variety of different functions. So thank you very much for watching.